Hello everybody, this is the first part of the mechanical ventilation lecture, and there are a total of 3 parts. Okay, so you will have 3 video lecture recordings. So in this first part, I'm going to discuss the concepts and principles of mechanical ventilation and then the indications of mechanical ventilation. Then in the second part, we'll talk about common modes as well as capnography, and then in the last part, about principles of weaning as well as effects and complications of mechanical ventilation on the body, specifically on the cardiovascular and pulmonary systems. We are still using Main and Dennehy as the main textbook, so these are the required readings for all 3 parts of this lecture on mechanical ventilation. But before we begin, let's review. We're going to review some respiratory physiology because I'm going to assume it's been some time since we've talked about respiratory physiology, and your understanding of respiratory physiology is important for your understanding of mechanical ventilation. So you need to understand how you breathe before you can understand what happens when you are put on a machine to help you to breathe. Okay, so the first thing. Okay. One of the things that you need to know is whether breathing is producing enough gas exchange to keep a person alive is the ventilation that the breathing is producing. Okay, so we are really looking at how your body functions in terms of getting the air into your lungs as well as leaving your lungs. So when we express ventilation, we usually express ventilation as minute ventilation, and the definition is on the screen. And the minute ventilation is the product of tidal volume expressed in liters as well as frequency, which is how fast or how slow you breathe in a minute. So therefore, the unit for minute volume is liters per minute. So then how do we know whether someone is ventilating well or breathing well? Okay? So we monitor that by taking blood samples from the arterial bloodstream to measure the amount of carbon dioxide in that arterial blood sample. So, and that's the reason why you need to learn about arterial blood gases. Okay? And for a given level of carbon dioxide produced by your body, okay, you need to know that the amount of carbon dioxide in your body is inversely proportional to the level of ventilation. Okay? Purely because carbon dioxide is very soluble in water, and therefore it actually diffuses through the blood-air barrier very, very quickly, okay, in and out. So if you breathe very quickly and deeply, okay, hyperventilation, increase in minute volume or minute ventilation, then your carbon dioxide levels in your bloodstream will decrease. Okay, the term used is hypocapnia. Okay, hypocapnia. Then conversely, if you have decrease in minute volume or minute ventilation, hypoventilation, then carbon dioxide will be retained in the bloodstream, okay, with increased PaCO2. Then the term used to describe that is hypercapnia, okay, or hypercarbia. Okay. So another concept for you to know is about pressures. You need to know the pressures within your respiratory system or respiratory physiology that helps you to breathe. Okay, some of the concepts you will include or kind of remember will be the pressure at the airway opening, okay, and then the pressure within the alveoli or in the lungs, okay, and then also the pleural pressure, okay, because it is your thoracic musculoskeletal system that actually works on the pleural pressure that creates a pressure gradient, okay, such that the pressure within the lungs is lower than the pressure outside the lungs. So therefore, a pressure gradient is created that allows air to move from a point of high pressure to the point of low pressure, creating inhalation. Okay? And you should know by now that inhalation is an active process. Your musculoskeletal system works on your thoracic cage and therefore creates this pressure gradient. And then when your muscles relax, exhalation is passive, and therefore passive recoils happen. Your ribs relaxes, your muscle relaxes, and therefore press onto the lungs and allowing air to move out from the lungs into the atmosphere. So when we look at this diagram, okay, we are talking about, this is the diagram for you when you breathe in and out, like you and I, okay? So during inhalation, as I said, your rib cage, your chest wall will move, okay? Remember the bucket handle movement created by your ribs, and your diaphragm contracts and becomes flatter, allowing your thoracic cavity to increase, okay? By increasing your thoracic cavity, then it actually increases or rather it produces a relatively negative pressure within the pleural space. Okay, so you can look at this, the pleural pressure. Okay, at rest, okay, is at -5. So when you start the inhalation process, okay, it becomes more negative. Okay, and this more negative pressure is of course then translated into the lungs, creating a pressure gradient, which means the pressure here is more negative than the pressure outside. So then air flows from the pressure of higher pressure or through to a point of lower pressure, and therefore inhalation happens. Okay. So when you exhale, when your thoracic cage relaxes, your ribs come down, your diaphragm comes back to the dome, relaxed phase, it pushes onto your thoracic cavity, and therefore creating a more positive pressure. Okay, so this more positive pressure then pushes the air from inside the lungs to outside the lungs, and therefore exhalation occurs. So therefore, to conclude this review, some points to remember, okay? Gas flow and pressure gradients. You need to understand as you breathe in and out, you need to know, of course, air flows from high pressure point to a low pressure point or through a pressure gradient. So you need to remember then, because of this pressure change, air flow happens. And when air flow happens, then there is volume change. That explains the volume change within your lungs, okay? Or your tidal volume change from inhalation to exhalation. Okay. Some caveats to remember at the end of inhalation or exhalation. So if you take a deep breath in and hold your breath, or when you exhale and hold your breath, okay, keeping your mouth open, not blocking your mouth, not closing your glottis, there is no airflow. Okay, then because the pressure across all the conducting airways are equal, and because no pressure gradient exists, so therefore there is no change in volume as a result of this non-existing pressure gradient when you hold your inhalation or when you hold your exhalation at the end of the breath. Okay, so we're going to then proceed to talk about concepts and principles. So let's start with the common terms used to describe, or the common terms used in mechanical ventilation. Okay, so in mechanical ventilation, the units of pressure preferred is centers of water, cm, H2O. Okay, of course, you know a lot of other units of pressure. Okay, you have the millimeters mercury, you have kilopascal, which is the SI unit, as well as atmosphere. Okay, knowing that 1 atmosphere at sea level is equals to 760 millimeters mercury, or equals to 1034 centimeters water. Okay, so I need to stress that when we say pressure, okay, when you read 0 centimeters water, positive 5 centimeters water pressure, positive 10 or plus 10 centimeters water pressure, okay, or negative 5 or negative 10, we are talking about it being referenced at 0, okay, when it's at sea level at atmospheric pressure. Okay, of course, you know that unless we are in outer space, we will not have a pure 0 pressure. So on Earth, at sea level, okay, the pressure of 0, when you use it to describe mechanical ventilation, we are referring to that 1 atmosphere at sea level, okay, which is 760 millimeters mercury or 1034 centimeters water. Okay, for units of volume is milliliters or liters. So most time when we usually use milliliters to describe tidal volume, okay, as the preferred unit of volume for tidal volumes. Then you also need to know about common terms used to describe lung characteristics, and there's this term called compliance. Okay, compliance refer to the opposite of elastance. Okay, elasticity refers to how well something returns to its original shape when it's stretched or pulled or distorted. But compliance refers to distensibility. How can something get stretched? Okay, so the more compliant something is, the more distensible or stretchable that thing is. Okay, if something is less compliant, then it's harder to stretch or harder to distend. Okay, and then this is the mathematical formula for it. Compliance is equals to change of volume, okay, over the change of pressure. So the change of volume that corresponds to a change in pressure. And because of this, volume milliliters, pressure cm water, then the unit of compliance is milliliters per centimeters water, or liters per centimeters water. Okay, so these are some reference points, okay, but you don't have to memorize this, but you should know what this formula is. Okay, compliance is equals to the change of volume that corresponds to the change in pressure. Okay, another lung characteristic that you need to know is airway resistance. Okay, and this refers to the change in pressure, the pressure between your mouth and the gas exchange area, which is the alveoli. Okay, the pressure at the airway opening and the alveolar pressure. Then divide that by the flow through the airways. Okay, so we are talking about how hard or how easy for that air, the volume of air, to move through the airways in order to effect that volume change within the outline. Okay, so the higher the airway resistance, then you will need a higher pressure to create a given change in volume. Okay, if there is a lower airway resistance, then you will need a lower pressure to effect the same given change in volume. Okay, so the unit of airway resistance is pressure, centimeters of water, by flow, and in this case, the flow is expressed as liters per second. So airway resistance, the unit of measurement is centimeters water per liters per second. And this is the approximate airway resistance value, but of course it changes all the time. Okay, so you have to understand that you have your own airway resistance, you and I. The moment the air enters through our nose or the mouth, and it has to go through the different airways, the upper respiratory airway into the lower respiratory airway, the trachea, then into the bronchi and the bronchioles, and then into the alveoli. It has to go through different sizes of airways. All these sizes of airways in terms of diameters change from wide to narrow, creates airway resistance. Okay, and then therefore airway resistance is not a uniform thing across the entire lungs. Okay, at different regions of your lungs, depending on what airways it is, the length of the airway, the diameter of the airway, how narrow, how wide, determines the airway resistance. So an example to use is if you have asthma and you bronchoconstrict, in other words, your airways get narrower, okay, then you will have higher airway resistance because you will need a higher pressure to push through that narrowed airway in order to create volume change. Okay. We've talked about compliance and then we've talked about resistance. So putting them together, the product of compliance and resistance for an alveolar unit is the time constant, and we've already discussed time constant before. Okay, we're in your year 2 module. So the time constant refers to the amount of time required to fill or empty a lung unit. Okay, so we already know different lung units in the different regions of your lungs. Okay, have different time constants. So your lung units in the upper chest versus the lung units in your lower chest will have different time constants because they fill differently. Then in a disease state, this is even more significant. Okay, because in a disease state, okay, alveoli may become more or less compliant depending on the pathology. In other words, it becomes more, okay, if it's more compliant, it's less stiff. If it's less compliant, it's more stiff. Okay, and then also the small airways also contribute to increased resistance, and therefore a diseased or an alveolar unit affected by pathology may have a different time constant compared to an alveolar unit that is not affected by pathology. Okay, so those are the common terms used, as well as characteristics of the lungs of ventilation that you need to know. Okay, then let's talk about mechanical ventilation terms. Before I talk about mechanical ventilation terms, let's talk about ventilation terms. So categorically, ventilation can be categorized into negative pressure ventilation. So what you and I are doing right now, as we breathe in and out, we are doing negative pressure ventilation because we create a negative pressure within our lungs, okay? Negative relative to the atmospheric pressure that you are breathing in, and then creating that pressure gradient, allowing air to move from outside the lungs into the lungs. Okay, that's negative pressure ventilation. The other type of ventilation is positive pressure ventilation, okay, which will be discussed in the next two slides. So negative pressure ventilation, when mechanical ventilation first started, this is the prototype. This is the iron lung, and the iron lung was created because of the polio pandemic that happened in the early 20th century, okay, in the early 1900s. Okay, so what this does is essentially you put the entire person inside the iron lung, okay, and there's a bellow here that actually then creates the negative pressure within the chamber where your body is, okay, and when the negative pressure is created, it actually creates that negative pressure within the thorax, allowing air to move from outside, okay, which is a higher pressure point, to the point of lower pressure. Okay, so the bellow causes the air pressure in the lungs to rise and fall, and the patient's lungs are aided in drawing in air. Okay, of course, you know that this particular form of ventilation is very debilitating to a person. Yeah, so graphically, this is how the negative pressure ventilation works. Okay, if there is still such a kind of mechanical ventilation called negative pressure ventilation, which is almost never used, then this is how it works. Okay, you have a mechanism that creates sub-atmospheric or negative pressure within the chamber, and this negative pressure is also created within the thorax. Okay, so negative pressure here, it pulls the thorax up, okay, yeah, and then therefore also creates a sub-atmospheric pressure within the lungs. Okay. So this pressure, being sub-atmospheric or negative, okay, is a lower pressure point compared to atmospheric pressure, which is a higher pressure point. So again, pressure gradient is created and air moves from atmosphere into the lungs, okay, like what you and I are doing right now. Then for positive pressure ventilation, so these are some of the examples of machines that you will see, okay, in Singapore hospitals. Okay, you probably may not see this. This is a rather old machine, but I know some units do use this machine. Okay, but you may see all variety of different mechanical ventilation in the intensive care unit that you may work in or you may go to when you are a student on the CP placement. So positive pressure ventilation literally is creating positive pressure that is pushed into someone's lungs. Okay? So when we look at the back mask ventilation, okay, the manual resuscitator, okay, this creates or rather delivers positive pressure ventilation. So this is something you need to remember. Okay, but is this mechanical ventilation? No, this is not. This is manual ventilation. You have to use your hands to press onto the bag in order to create the positive pressure that is pushed into someone's lungs. Okay, so when you are doing resuscitation using the manual resuscitator, this is something you need to be mindful of. Okay, don't press too hard, don't press too much. You may potentially burst someone's lungs. Okay. So graphically, this is what happens. Okay, when you do positive pressure ventilation, and this graphic on this figure, this is the figure 4 positive ventilation, if you think of this as the back mask ventilation or the manual back resuscitator, when you press onto the back, you create positive pressure. And this positive pressure is above atmospheric, right? So this creates a high pressure point compared to the pressure within the lungs. So pressure gradient is created and therefore air moves from atmosphere into the lungs because of the pressure gradient. Okay, so contrasting this diagram to the diagram in the review slides, okay, this is the diagram for positive pressure ventilation. So at rest, if you look at on this side where the laser pointer is, then at rest, intrapleural pressure continues to be at -5, right? Okay. Then when positive pressure is being applied in through the mouth or through an artificial airway into the lungs, okay, it pushes pushes air into the lungs because of the airway gradient or the pressure gradient. Then at the end of the inhalation, what is measured within the lungs as well as within the pleura, okay, is actually a more positive pressure, a pressure that is above atmospheric. Okay. When you exhale, then everything just relax, right? You release, you take off the positive pressure, everything else goes back to a static or relaxed state. Okay, and therefore air moves from, and because of the thorax and the diaphragm going back into a static state, it pushes against the lungs and creating a higher pressure point now within the lungs compared to atmospheric. The pressure gradient is created and therefore exhalation occurs. And in this case, of course, passively most of the time, unless you actively exhale. Some other mechanical ventilation terms includes all this, right? You know that you and I are breathing spontaneously, so those are considered spontaneous breath. But on a machine, you're also allowed to take spontaneous breaths, and we will differentiate that later. Okay, how do you differentiate a machine breath versus a spontaneous breath? I will discuss that later. Okay, and then there are the different ventilator modes. Okay, then regardless of what manufacturer or brand names, okay, they all fall into combinations or names of these. Okay, so in principle, these are the actual so-called generic names for the ventilation modes. But because mechanical ventilators are made by different companies and therefore they like to patent then some terms, and on different machines, the same mechanical ventilation term might be termed differently. Okay, so all these I'll discuss later. But don't worry about manufacturers' proprietary terms. Okay, generic terms, understanding the principles and the concepts are more important. Okay, then we will talk about the pressures in the next 2 slides. Okay, pressures that you need to understand in order to understand mechanical ventilation. So the first pressure you need to know is, of course, the baseline pressure. This is the pressure at the end of exhalation before inhalation. Okay, and this is the pressure read at baseline. And if this pressure is above 0, which is more positive than atmospheric, then we term that as positive end expiratory pressure, or the long PEEP, PEP, PEEP. Okay, now PEEP is important, okay, because then it keeps your lungs inflated in a relatively inflated state at the end of exhalation, and therefore helps to prevent alveoli from collapsing. And therefore, PEP increases your functional residual capacity. Okay, so when PEP is applied through a mechanical ventilation, it keeps your alveoli open at the end of exhalation, preventing alveoli from collapsing. Okay, so that's one function of applying positive and expiratory pressure. Okay, so then there are 2 types: extrinsic PEP or intrinsic PEEP, which is applied through the machine. You dial in the number, and therefore that is the PEP. Okay, normally is at it goes, of course, from units of 1 centimeters water to +2, +3, +4, +5, all the way to even +20. So that's extrinsic PEEP. Another concept is called intrinsic PEEP, when there's air trapping. Okay, and when there's air trapping and a person is not able to really fully exhale out all their inhaled air because of early collapse of the airways, then the air that is remained in the lungs or in the airways can impose a what we call intrinsic PEP or auto PEEP. Okay, is this concept important at this point in time? No. Okay, you need to know more importantly what is PEP, which is the positive baseline pressure. Okay, and what it does, it increases FRC. And when it increases FRC, because it does not allow the alveoli to collapse, it maintains the surface area for gas exchange, okay, allowing oxygen to diffuse through. So therefore, PEP is also used in addition to supplementary oxygen, FiO2, to improve or optimize oxygenation. Okay. Another pressure that you need to know is the peak pressure. Okay, the proper term is peak inspiratory pressure, in short PIP. Now, because PIP, PEEP, is very similar to PEEP, PEP, so it's easier to call it peak pressure. Okay, so the peak pressure then is the highest pressure recorded at the end of inhalation. Okay. So the combination of the pressure that is required to fill the alveoli as well as the pressure required to overcome air resistance is the peak inspiratory pressure. Okay, so if you express this, what it equals to, PIP, peak inspiratory pressure, is equals to the pressure required to force gas through airway resistance, we call it trans-airway pressure, and plus the pressure in the alveoli, okay, big A alveoli, at the end of the inhalation. So this is what peak pressure means. So graphically, if you look at this, the y-axis being pressure expressed in centimeters water, and then the x-axis, the horizontal axis, in time. Okay, so when you have a positive pressure ventilation being initiated or pushed into a person's lungs, positive pressure breath, the pressure rises during inhalation, okay, to the point of the highest pressure. So at this point, if we don't allow the patient or the person to exhale, we put a breath hold. Okay, then we notice that something happened. This phenomenon happens. Okay, the pressure rises during inhalation to PIP. We put in a breath hold. We don't allow the person to exhale. We notice that there is this pressure that's being measured called the plateau pressure. Okay, so suddenly you just stop the person from breathing out, and then there's a little bit of a dip, and then there's a flat pressure being measured, and this is that plateau pressure. Then you allow inhalation to occur. You take off the breath hold, then exhalation occurs passively, and the pressures fall back to the baseline pressure. Okay, so in this case, the difference between PIP and plateau pressure, this pressure, okay, is the trans airway pressure. Okay, I'll show you in the next slide. Okay. So concentrate on this this part. Okay, I mentioned earlier positive pressure breath, the inspiratory pressure increases until to the point of the highest point, which is the peak inspiratory pressure. We then don't allow the person to exhale. We put in a breath hold. Okay, then we notice, okay, graphically, hey, there is this flat point that's being measured, this plateau pressure. Okay, so the difference between the peak pressure and the plateau pressure is the trans-airway pressure. So back to the two slides before, yeah? Peak pressure equals to the pressure required that is required to force air through airway resistance, which is trans-airway pressure, as well as the pressure that is inside the lungs. In this case, the plateau pressure. Okay. Do we put in a breath hold all the time? No. Most practitioners or clinicians don't put in breath holds anymore. Okay. In the past, there are people who put in breath holds because there is a belief that when you hold in your breath, it may help with lung recruitment and may help with optimizing oxygenation. But that's been proven to be not as effective. So you probably won't see this kind of graphs on mechanical ventilators anymore. Okay, so just be mindful of that this is purely for you understanding the concepts of mechanical ventilation. Okay, now what's the difference between this graph and the previous graph? Now in this graph, okay, we are talking about two types of breaths within this particular graph. Okay, there is a mechanical positive pressure breath as well as a spontaneous breath. Okay, so this is the positive pressure breath. Okay, then this in black that I have circled is the spontaneous breath. Okay, how you and I might breathe. Okay, so let me erase all this first. So when we look at this, and then of course the difference between this graph and the previous graph is that now we've raised the baseline pressure from 0 to now plus 10. So we have now added in a PEEP. It's an elevated baseline pressure of, on this graph, 10 centimeters water pressure. Okay, so then of course on this graph also you have this little thing called the assist effort. Okay, this assist effort is a little dip below the baseline that tells us that the patient is actually trying to take in a breath, suck in a little bit, and when the machine detects this effort, it so-called triggers the machine to deliver the positive pressure breath or the mechanical positive pressure breath. Okay, now in this graph, this particular person on this so-called mechanical ventilation mode is allowed to breathe spontaneously. Okay, and a spontaneous breath in this pressure time graph, the shape is sinusoidal. So this is how it is. When you take a deep breath in, you create a negative dip pressure. Then at the end of exhalation, you exhale, then the pressure becomes positive to exhale, and then it goes back to baseline at the end of exhalation. Okay, so contrast this, the spontaneous breath graphic to the positive ventilation graphic. Okay, positive ventilation like this. Yeah, negative, or rather spontaneous breath is negative pressure ventilation, sinusoidal, so it creates that negative pressure and then the positive pressure during exhalation. Okay, yeah, so will people be put on a mechanical ventilation and allowed to just breathe on a raised baseline and then breathe spontaneously? Yes. Okay, and that is called CPAP, and we will discuss that in the second part of this lecture. So some points to remember. Okay, I iterate again that air, like any fluid, flows down a pressure gradient, a point of high pressure to low pressure. Again, it's because of this change in pressure, then there's airflow. Okay, because of airflow, then there's a resultant lung volume change. Okay, you need to understand that all modes of ventilation is because of a change or increase in transpulmonary pressure. So whether it's negative pressure ventilation or positive pressure ventilation, is all about increasing the transpulmonary pressure. In order for you to inhale, okay, there needs to be an increase in transpulmonary pressure. So whether you are decreasing your pleural pressure by you and I breathing right now, taking a deep breath in and breathe out, or during your normal breathing, or by increasing your alveolar pressure through the addition of positive pressure in the form of mechanical ventilation. Okay, it's all about increasing transpulmonary pressure. We also talked about characteristics, okay, because normal people won't be put on mechanical ventilation. So usually people with pathology or has the need will be put on mechanical ventilation, and you need to understand how your lung characteristics changes or changes within the lung characteristics affects ventilation. Okay, so higher compliance means it's less stiff, okay, then therefore more stretchable will result in a larger volume change. Okay, because it's less stiff, then therefore less pressure is required. Then, of course, conversely, lower compliance means the lungs is more stiff, it's harder to stretch, and therefore you have a lower volume change, but a higher pressure is required to push through, to stretch that so-called lower compliant lungs. Yeah. Then, in terms of airway resistance, simple concept: increase in airway resistance means you need more pressure to push through, and therefore it will increase vocal breathing. Okay. Simple experiment of airway resistance. Take a straw, a very narrow straw, and try to breathe through it. Just by breathing through a very narrow straw, you are increasing the airway resistance that you're feeling, and therefore you have to actually breathe harder, and therefore it increases vocal breathing. Contrast that with breathing through a bubble tea straw, the big straw that you use to suck the bubble up, that big straw. Big straw versus small straw. Big straw has less big straw has less airway resistance. Small straw has more airway resistance. Okay, so use that for you to really experiment how it feels like in terms of the effect of airway resistance on the work of breathing. We talk about all the some of the terms and pressures. And also lung characteristics. So let's move on to phases of the breath, and this is actually the same as your normal breath also. Okay, if you use this to describe what you and I are doing right now, okay, spontaneous breathing, your brain triggers the breath, okay, triggers the initiation of the breath, okay, then inspiration happens, your diaphragm descends, your rib cage rises, Parkinson movement, okay, then when you reach the volume that is required, it just stops. It ends the inhalation, what we call cycling off, and then exhalation occurs passively. So likewise, in mechanical breathing, we need to program the ventilator, which is a machine, to deliver the breath. So there should be a trigger. Okay, a trigger can be either triggered by time. So I set a person to breathe at a rate of 12 breaths per minute. So therefore, 60 seconds divided by 12 is 5 seconds. Every 5 seconds, it triggers the breath. Okay. Then we need to then also put in the parameters to describe the inspiration, the limit. So whether it's delivered by pressure, we need to limit the pressure. If the breath is delivered by volume, we need to limit the volume. So either the machine has reached the volume or the pressure over a particular period of time, what we call the inspiratory time, then the pressure is said to have been delivered, okay, by the inspiratory time that is set, or by the volume, by the inspiratory time that is set, and by the pressure or volume that is also set. Okay, so when the time is up, okay, with the pressure delivered or with the volume delivered, then the inhalation ends. Okay, what we call the machine then cycles off into exhalation. Everything ceases, exhalation occurs passively. Okay, then the next breath occurs. Already talked about earlier that there are different breath types, mandatory breaths, okay, or machine breath. So it's probably easier to remember this as machine breaths because it's when the machine initiates, delivers, and stops the breath. So everything is controlled by the machine. Then there is the assisted breath, where it's a combination of spontaneous and machine breaths. So in assisted breaths, what we call assisted is the patient actually initiates the breath, but because the patient is not strong enough to breathe on his or her own or on their own, then it is assisted by the machine. So the person initiates the breath, and then the machine assists by delivering and stopping the breath. Okay, then the last part, the spontaneous breath, what you and I are doing. we initiate and we stop the breath. But in this case, of course, when we're talking about spontaneous breaths on a mechanical ventilator, we're talking about the person initiating and stopping the breath while on the mechanical ventilation. And in this case, the breath may be supported by the machine, okay, through pressure, and we'll talk about that in the second part, the second lecture. But it's not delivered or controlled by the machine. So the person can initiate or determine when he wants to start breathing, when he wants to stop breathing. The inspiratory time can vary, the depth of the breath can also vary. Okay, and that's spontaneous breath. Okay. So how do we then determine the difference between a machine breath and a spontaneous breath? Okay, as long as a person can control the timing and the size of the breath, like what I said earlier, okay, can control the inspiratory time, can control the volume or the size of the breath, then it's called a spontaneous breath. Okay, otherwise, it's always a machine breath. So even an assisted breath, let's go back to the previous slide, which I can't. When you go back when you refer to the previous slide, an assisted breath, the patient initiates the breath, but the machine delivers or stops the breath. It is still a machine breath. Okay, so the only difference is this. Yeah, only if a patient can control the timing and the breath, can initiate, okay, and can stop, and then also can control the size of his own breath, that is called a spontaneous breath. Yeah, so then that essentially is the distinction between defining whether the person is on a mandatory mode of breathing or on a spontaneous mode of breathing. Okay, so that's about all we have in terms of the main concepts and principles of breathing. We have positive pressure ventilation. Okay, someone who is not able to breathe or his or her own, or needs help to breathe on their own, will be put on mechanical ventilation. And the mechanical ventilation can be either invasive or non-invasive. Invasive means the person has been put on the artificial airway, which you have covered in Meredith's lecture, or non-invasive when it's delivered through a face mask. Okay, and then there is spontaneous breaths and machine breaths. Okay, so then within machine breath, there are different type of modes which we'll cover in the second lecture. Okay, so then before we go to the second lecture, I need to talk about what mechanical ventilation does. Okay, which, in other words, the physiological objectives of mechanical ventilation, what it does. Okay, three main things. Okay, it supports and manipulates gas exchange. Okay, which means it helps to manage respiratory failure, whether it's type 1 or type 2. Okay, so and then of course it helps with increasing PaO2 because mechanical ventilation can help to deliver supplementary oxygen, but also because of the pressures that it delivers, especially the PEEP, the positive baseline pressure, it helps to optimize oxygenation. Okay, and of course we can manipulate the machine to manipulate how much you breathe, and therefore helps to normalize PaCO2. Okay. Second one, increased lung volume. We've already talked about how PEP increases FRC, and also then therefore the positive pressure helps to prevent and reverse atelectasis. Okay. And the last one is really to decrease vocal breathing. And in order for therefore it takes off your normal respiratory physiology's work, so that the machine helps you to breathe, and therefore you can rest. Yeah, so therefore decrease vocal breathing. Last slide, the indications for mechanical ventilation. So if someone comes into the emergency room breathless, or then the emergency physicians or an ICU physician have to decide whether the person needs to be intubated or initiated a mechanical ventilation. These are some of the standard criteria. Number one, if a person is not breathing, right? An artificial airway will be placed, and therefore the person will need mechanical ventilation to help the person to breathe. Okay, then determine the cause of the apnea. Okay, apnea means absence of breathing. Second criterion, acute ventilatory failure, the type 2 respiratory failure, when there is hypoxemia and also hypercapnia. That's type 2 respiratory failure. Okay, and the person is not able to oxygenate well, hypoxemia, and not able to ventilate well, hypercapnia, then mechanical ventilation can come in to help with correcting the respiratory failure. The third one is impending ventilatory failure. And this criterion essentially means, do we need to wait for the person to be in true type 2 respiratory failure before we implement mechanical ventilation when we know that the patient is going to go into acute type 2 respiratory failure? The answer is no. Okay, if we know the patient is it has impending type 2 respiratory failure or ventilatory failure, then that is a good reason to put the patient on mechanical ventilation. Then the last part, this is essentially type 1 respiratory failure. Okay, when we are talking about the patient has low saturation, has low PaO2, is hypoxemic, but is not responding, refractory, not responding to normal treatment, which means just oxygen therapy. You put the patient on 100% non-rebreather mask, the patient is already receiving 100% oxygen, and the patient has signs of increase of vocal breathing, is already going to be getting more and more tired, eventually going into type 2 respiratory failure, then that is also a standard criterion for mechanical ventilation. Okay, so we've covered the three physiological objectives of mechanical ventilation in the earlier slides. Now we covered the 4 standard criteria for mechanical ventilation. Okay, and that wraps up this topic. And in the next video, we're going to talk about the types, the modes of mechanical ventilation, as well as capnography. Just a note, please, to prepare for the lab related to this topic, please read the required readings, review the lecture recordings, and then also the student handbook materials. Okay, thank you.